Hello everyone and welcome to the first session of digital design. Through the series of these videos, we will explain how digital design works, how each and every experiment is conducted. The course material is related to whatever has been taught in Expt Dubai campus. We start with experiment 2, which will include 3 runs. The first run will be function implementation. Second will be what is parity, what is even parity, what is odd parity, and third will be what are gray codes and how are they implemented. Starting with run 1. Run 1 includes first of all a truth table. Truth table can be considered a set of inputs giving a set of outputs, and those outputs are written in the form of f, which is the function. You have inputs as A, B and C, and F is the output. Now these are written as, because any binary number is written in the form of 2 raised to the power 0, then 2 raised to the power 1, 2 raised to the power 2 and so on. So similarly, you will have, this is 1, 2 and 4. So one number of 1 bit change in the first column, 2 bit change in the second column, and 4 bit change in the third column. That means that one change means 1011, then 0101, one change. Then two changes after 2, that means 2 zeros, 2 ones, 2 zeros, 2 ones, and similarly after 4 means 4 zeros, 4 ones. Because it is a 3-bit input, so the total number of combinations that will be there are 2 to the 3 which are ready. That is with the input. Now the output, let's suppose that in our example the output is something like that. As apparent, because these are 3 inputs, so corresponding decimal conversion of these will be 0, 1, 2 and then 7. Okay. So if this is 1, that means the output is 3. This is 5, 6, 7. So there is a concept of midterms in maths terms. Midterms means that we'll explain that in detail, but generally any function can be written as sum of product or product of sum. This is known as sum of product form, and this is product of sum. In sum of product form, whatever outputs are high, means 1 in the function, are written in the form of sum, and whatever outputs are low are written in POS form. So POS form will have 0, 1, 2 and 4 in the function writing format, and whereas the POS form or SOP form will have 3, 5, 6 and 7. Now another notation for this is this stands for SOP form. SOP form we write small m, and in the subscript you will have 3, m5, m6 and m7. So a function can also be written as something like this in SOP form, whereas for POS form you will have capital denotation. So capital M0 plus capital M1 and so on. So that will be denoting POS form. Now starting with how this function is written in the form of SOP. So let's say if I have f, so the way SOP form works is that if I have 0, that will stand for a bar. If I have 1, that will stand for the same number. So if I say I have A, B, C, that means I have 1, 1, 1. If I have 0, 1, 0, that means I have A bar, B, C bar. So a 0 will stand for a bar, or a 1 will stand for the same. So I can say, if obviously I just need to see the ones for SOP form. So 1 stands for 0, 1, 1, that means A bar, B, C. So A bar, B, C is my first term. And similarly, the other terms are taken by adding all the other terms which are 1. So A bar, B, C plus A, B bar, C plus A, B, C bar plus A, B, C. The next step in after getting the function is to simplify it using Boolean algebra. There are various formulas, methods and all those things. We'll discuss them and then simplify it. So first of all, it includes this formula which states that x plus y z can be written as x plus y into x plus z. Next is b into b bar is 0, b plus b bar is 1, b, a, c, anything. Then a into b bar, these two are known as De Morgan's law. De Morgan's law. So a into b bar is A bar plus B bar. A plus B bar is A bar into B bar. These will be used in a bubble pushing method, which will be described later. Now, coming to this, we have four terms and they have to be simplified using Boolean algebra. So, first of all, we'll combine A bar BC and ABC. BC taking common A plus A bar, then the rest remains as it is. A plus A bar from this formula is 1 cancels out. So, because BC into 1 will remain BC. So, BC plus these two terms. Then C is taken common from these two. So, that is left with C times B plus AB bar plus ABC bar as it is. Then B plus AB bar using this formula can be written as B plus A into B plus B bar, and this remains as it is. This becomes 1. So we are having now BC plus AC plus ABC bar as it is, which can be written as again AC taken out plus B common C plus AC bar, again using the same formula, simplifying it and finally getting AB plus BC plus AC. Note that sum of product and product of sum forms are inverse of each other. So, if we have sum of product form in the simplified manner, then taking the complement of it will give, and simplifying it will give the product of sum form. So, that has to be done. As it is, you can see that the numbers includes from 0 to 7, right? So, some of the numbers will be in the ST form, the other remaining ones will be in the POS form. That's how it is done. Alright, now we'll start with the function implementation of this function that we just received. So the function is AB plus BC plus AC. So if the inputs are A, B and C, the output should finally be AB plus BC plus AC. This part. Okay. So we will initially implement it using AND and OR gates, and later we'll use NOR gates and NAND gates to implement the whole circuit. That will come under bubble pushing. Okay. So A, B. This is AND gate. So the output will be AB. Now BC means again BC using AND gate. The output is BC. And lastly we have AC. So again using AND gate gives AC. AB plus BC plus AC. They have to be added, right? So use OR gate. The output is AB plus BC plus AC. Note that we may not have a 3-input OR gate always. So in case we do not have it, we use 2 inputs OR gate and take the output of this OR gate with the third one to get AB plus BC plus AC. So this is how the circuit is implemented. Next we come to using NAND gate or NOR gates to convert all of these gates into that. Okay, so let's see. The few things to note over here is I will try or I will make these in the form of a circuit. So De Morgan's law can be written as A dot B bar is A bar plus B bar, right? So if I want to implement it, then A input, B input, bar. Bar can be just a denotation. This will stand for a bar. So if input is A, output will be a bar. So this is similar to having an invert gate. So A, given A, you get A bar. So what I can say is AB multiplied bar is equal to A bar plus B bar. So you have A, you have B, A bar, B bar plus. These things will be important. So this is one. Next is the second one, which is A plus B bar. So A plus B bar means you have A, B, and A plus B bar is equal to A bar into B bar. So you have A bar B bar multiplied, or invert or is equal to invert and is equal to or invert, and invert or is equal to and invert. That's how it's called. So these will be used in circuit implementation. One more thing that is important to note over here is that how inverter works. You have seen that there are two ways to write it. There are much more other ways as well. You can also say that if A is the input and you give both the inputs to a OR gate, you get A bar. Check it out. And similarly, if A is given to a NAND gate, you will again get A bar. So another way to say the same thing is I have this, or I have this or this. They all mean the same thing. So all these are synonymous. Wherever you have a bubble, I can replace this anywhere. This has importance because when we do this or when we implement using NAND and OR gate, then we will realize that some places we are left with just bubbles, and wherever we are left with bubbles, we can replace it with that. These are NOR gates and NAND gates. Okay, so how does bubble pushing work? Fine, we have A bar and B bar. Alright, now we start with what is bubble pushing. Bubble pushing has one basic idea. I have any circuit in the form of NAND and OR, and I want to use NAND completely, complete the whole circuit using either NAND gates or NOR gates. And why only these two? Because they are universal gates. Universal gate means you have any gate that can be converted to NAND or NOR gates. Alright, so one more thing, that this is 7404 or 7408 AND gate, and this is 7432. This is 7402, and this is 7400. Name of the gates, because we will actually in lab use ICs. IC will be looking something like that. It will be an 16 pin or 14 pin IC. You start numbering from here, and then 1 to 7 or 8 comes here, and then 8 or 9 onwards till 14 or 16 comes over here. So this is how it is numbered. This can be 7404, 740832 or anything like that. This is how IC looks like. So in reality, you do not have gates anywhere. You have internal circuit of an IC in the form of gates, which will have something like this. Two gates on this side, 2 gates on that side. That's how internally ICs are connected usually. Okay, so now the basic idea is that I want to convert all of them into say NAND. Before this, you know that if I do an invert, then I do another invert again, then I get the same thing. If this is A, this becomes A bar after this, and after this again A. So I get back the same product. Fine. Now I want to convert this into NAND. NAND means a bar after AND. So sorry, a bubble after AND. So this becomes a NAND gate. Now because we have changed this into a NAND gate, we need another bubble to get the same output. Otherwise the output gets changed, obviously. Similarly, I have made this a NAND gate, so I need one more bubble to cancel it out. Similarly, one more bubble to cancel this out. Bring all of them together, over here, and I can remove it from here. So, this is normal bubble pushing. If you see from this formula that we had, this is similar to an AND gate, no change. So, instead of having this, I can directly make an AND gate. So, this is an AND, this is an AND, this is an AND, this is an AND. Finally, we have one bubble over here and an OR gate over here. An OR gate over here. Wait, let me zoom in. So I have a bubble, an OR gate, and the rest all of the circuit is NAND. Only this is there. Finally, I need to make something like this. This has to be made something like this so that I get an AND gate. Fine. So make one bubble over here. This becomes an AND, but because you put another bubble, so put one more bubble to cancel it out. Fine. This becomes an AND gate. Now this is left out. As stated over here, if I have any bubble, a bubble can be replaced by something like this so that it again becomes an AND gate. All of the circuits become an AND. So this can be replaced by this. So all of the ICs present in this, all of the gates present in this are NAND. The same way we can do circuit implementation using all of the gates as NOR gates. Fine. So this becomes NAND, this becomes NAND, this is NAND. You have this also as NAND, and you have bubble over here. Bubble is this. This is how bubble pushing is done. So this has been implemented using bubble pushing. If we make the whole circuit again, just for simplicity, we will have this. Okay. So A, B, C, you have one NAND gate, then B, C, another NAND gate, then A, C, another NAND gate, then these two have been connected with another NAND gate, then there is another NAND gate, and finally these two have been connected with the NAND gate. So this also gives A bar AB plus BC plus AC. Same output as this. No change. So this and this, both the circuits are the same. I mean, it can be implemented using AND or AND NOR as well. This is bubble pushing, and this is what is required in function implementation. So any general type of question is that if you are given a function which can be in the form of a truth table or those SOP POS forms, something like this, then write the function, simplify it using Boolean algebra or K-maths, which will be told later, and then implement the circuit and finally use it or implement it using only NOR gates or only NAND gates. This is how it is done. So next we come to parity. Okay. The next run is about parity. Parity includes two types of parities: odd parity and even parity. What does it mean exactly? Odd parity means that if the set of inputs given are having odd number of ones or odd number of highs, then the output is high. If it is even number of highs, then the output is low. So the same is true for even parity. Even parity means if the odd number of inputs are high, if even number of inputs are high, then the output is high, and if odd number of inputs are high, then the output is low. We'll discuss about that. So suppose we have take any combinations. So we have 2-3 combinations over here. Over here, as it is visible that there is 3 input and B is high, so only one input is high. B1 is odd, so odd number of inputs are high, so output is 1. And here, even if number of inputs are odd number of inputs are high, so output is low. For even parity, this is odd parity. Odd parity. Similarly, 2 inputs are high, 2 is even, so this will be 0, this will be 1. Again, this will be 1, this will be 0, this will be 1, this will be 0. Now, XOR gate, denoted by this, XOR gate is an odd parity generator, and an XNOR gate, which will be a complement of this gate, is an even parity generator in general. So, if an implementation comes for a 3 input ABC, first of all read them to XOR, then read this along to XOR, will give an final output as A XOR B XOR C. Now, one more thing, if you want to make XNOR out of it, because XNOR is a complement of XOR, so what we can do is we can give another input to this. See, the general idea, because this is used everywhere, logics are based on this. XOR means XOR means odd parity. Odd parity means that if the number of inputs are odd, if odd number of inputs are high, then the output will be high, right? So if this is A, then to get A, I should have 0 over here. 0 will mean that if 0 is given, 0 or ground or low, anything, if a 0 input is given along with A, then the output will remain A. And if 1 is given along with it, then the output will be A bar. So the idea is, here I have A XOR B XOR C. If this is treated with some external control bit, because that's how it's called, if control bit say L or any other input which can be either VCC or ground, if it is treated with this, so we will have another XOR gate, and if this is 1, then the output will be A XOR B XOR C bar, or in general, sorry, single bar. This is XNOR. So this is how XNOR can be generated from XOR. This is about parity. Next we discuss about gray codes. The next graph is about gray code. Gray code means a set of codes in which one bit or one number to the second binary number is having only one bit change. So say for example you start with 0000, so the next number should have only one bit change. One bit change can be from MSB to LSB anywhere, but just one bit change. So let's say we start with LSB and change just one bit. So from 0000 to 0001, one bit change, 0 to 1. The next one should have only one bit change. So just note, by general convention, this is decimal to binary, this is 0, this is 1. So if you make the next one as 2, then it will be 0010. Note that you had 0001 over there. 1 changed to 0, 0 changed to 1, 2 bits change. So that's why leave 1 as it is, change 0 to 1, so single bit change. Similarly, now over here, 1 changes to 0, 1 remains as it is, so again 1 bit change. 0 as it is, 1 as it is, 0 to 1 bit change. And this is how the gray code works. If you see it formula wise, so if any number can be written finally as B3, B2, B1, B0, so if this is B3, B2, B1 and B0, then in gray code, G3 will be B3 directly, that is the same digit. G2 will be B3 XOR B2, XOR of these. G1 will be B2 XOR B1, G0 will be B1 XOR B0. So if let's say if I take this, so G3 is equal to 0, G2 will be XOR of these two. XOR, as stated, it is odd parity. Odd parity means both the inputs are 0, so output is 0. G1, these two XOR of these will give me 1, and G0 XOR of these will give me 1. So the gray code for this number, if this is considered to be binary, is 0, 0, 1, 1. That's how gray codes are done. Now, the standard logic using this formula for generating a function for gray code will be if I have 4 inputs as B0, B1, B2 and B3, then B0, B1 XOR gives me what this is G B0, B1 gives me G0. Then B1, B2 XOR gives me G1. So this is G1. B2, B3 XOR gives me G2. And B3 directly gives me G3. Now finally you get gray code. And it's important that you have resistors. They're just made for the purpose so that any gate is not left out directly. You should have resistors to make the circuit proper, and after that, LEDs have to be connected, which are, this is how it is symbolized. So in a breadboard, this is how the circuit